Today we'll discuss CMI's 2018 paper, and this paper has some interesting questions. Now the first question, it says, consider an equilateral triangle ABC with altitude 3 centimeters. A circle is inscribed in this triangle, then another circle is drawn such that it is tangent to inscribed circle and the sides AB and AC. Infinitely many such circles are drawn, each tangent to the previous circle and the sides AB and AC. So the figure shows the construction after 2 steps. We need to find area of all such triangles. So the first result that we need in this question is we need to prove that radius of all these circles, they'll be in geometric progression. So what we'll do is we'll enlarge this triangle. Suppose this is your circle 1. Then this is suppose circle 2, and then this is suppose circle 3, and this point is A. It's your altitude, say D, and these points, they are B and C. This is R1, say this is R2, and this is R3, and this angle is 30 degrees. Now in all these 3 right angle triangles, sin 30 will be same. So suppose this distance is x. So for this first triangle we can write sin 30 as, for this first triangle will be R3 upon x. For the second triangle it will be R2 upon, and this length will be x plus R3 plus R2. And for this larger triangle, it will be R1 upon x plus R3 plus 2R2 and then plus R1. Now we know that if A upon B equals C upon D and equal to say E upon F, then A minus C upon B minus D must be equal to C minus E upon D minus F. So we'll use the same property to eliminate this x. So we'll write R2 minus R3, and here it will be R2 plus R3, and here we'll write R1 minus R2, and here it will be R2 plus R1. Now we'll use componendo dividendo. Then we can write 2R2 upon 2R3, and it will be equal to 2R1 upon 2R2. So from here we'll say R2 square equals R1 into R3, that is R1, R2, R3, they are in GP. So radius of all these circles, they'll be in geometric progression. So what we need to do is, in this question, we need to find this R1 and this common ratio, which is say R. So we know that length of this altitude is 3 units. And this point, it is in center, which is same as centroid, which divides it in the ratio 2:1. So that means this length, it is 2 units. So this length, it will be simply 2 units. Now sin 30 is R1 upon 2 and sin 30 is 1 by 2. So from here we'll say value of R1 is simply 1. Now for this second triangle, we can write sin 30, which is 1 by 2, and it will be equal to R2 upon 2 minus R1 plus R2. So we can write this as 2 minus R1 minus R2 is equal to 2R2. So we can write 3R2, and this is 2 minus R1. R1 is 1. So R2 is 1 by 3. So all these circles, their radius, they'll be in GP, and the GP is 1, 1 by 3, 1 by 3 square, and it goes up to infinite. We need to find sum of areas of all the circles. So sum of areas of all the circles will be pi r square. So it will be 1 plus 1 by 3 square, 1 by 3 to the power 4 up to infinite. So this sum will be pi a upon 1 minus r. So it will be 9 pi by 8 centimeter square. So that is the answer to this question. Now question number 2 says, Consider the following function defined for all real number x, fx equals 2018 upon 10 plus e to the power x. Now it says how many integers are there in the range of f. So we'll need to find range of f. So we know that exponential function is always greater than 0 and less than infinite. Now we'll add 10 to it. So it'll be 10 is less than 10 plus e to the power x is less than infinite. Now we'll take reciprocal, then we can write 1 upon infinite, which is 0, is less than 1 upon 10 plus e to the power x, and it is less than 1 by 10. Now we'll multiply it with 2018. So we'll get 0 is less than 2018 upon 10 plus e to the power x, and it is less than 2018 divided by 10. So we can write this function fx will lie between 0 and 201.8. Now this function, it is a continuous function. So it will take all the values between 0 to 2001. So number of integers in this range. So number of integers in this range simply will be 201. And that is the answer to this question. Now question number 3, it says list every solution of the following equation. Now we are given that cube root of x plus 4 minus cube root of x is equal to 1. So what we'll do is we'll let x as t cube. So we can write cube root of t cube plus 4, and then we'll take this cube root of x on the right hand side. We'll write 1 plus t. Now we'll cube both sides. We'll write t cube plus 4, and this is 1 plus t cube plus 3t square plus 3t. Now t cube, it will cancel. So we can write 3t square plus 3t minus 4 plus 1 equals to 0. So we'll get this equation as t square plus t minus 1 equals to 0. Now we'll simplify this. We'll get t as minus 1 plus minus under root of b square minus 4ac upon 2a. So it'll be minus 1 plus minus under root 5 upon 2. Now x is t cube, so we'll need to find x. So x simply will be t cube, which is minus 1 plus minus under root 5 by 2 whole cube, and we need not simplify this answer. Now question number 4 is we'll need to solve this integral, which is integral from 0 to pi by 2 dx upon under root sin x plus under root cos x to the power 4. So let this be I. Now we'll take under root cos x common, then we can write this as 0 to pi by 2, and then it'll be under root cos x to the power 4, which will be cos square x. So 1 upon cos square x will be secant square x. So it'll be secant square x dx upon, and here it will be under root of 10x plus 1 to the power 4. Now it's a simple substitution question. So what we'll do is we'll let under root 10x plus 1 as t. Now we'll differentiate. We'll get 1 upon 2 under root of 10x and secant square x dx as dt. So from here we'll write secant square x dx is 2. Now under root 10x is t minus 1. So it'll be 2t minus 1 into dt. Now we can write this integral as 2t minus 1 dt upon, and here it will be t to the power 4. Now when x is 0, t is 1, and when x is pi by 2, t is infinite. So this integral will be from 1 to infinite. So we can write this integral as from 1 to infinite 2 upon t cube and minus 2 upon t to the power 4 dt. Now we'll integrate. We can write this as 2, and it will be t to the power minus 2 upon minus 2 from 1 to infinite, and here it will be 2 t to the power minus 3 upon minus 3 from 1 to infinite. So we'll put the limit. So when t is infinite, 1 upon t is 0. Then it will simply be 1, and then minus t is infinite, it will be 0. Then it will be 2 by 3. So answer to this question is simply 1 by 3. Now question number 5, it says list in increasing order all positive integers n less than or equal to 40 such that n cannot be written in the form a square minus b square where a and b are positive integers. Now we know that if n is an odd number, then we can write n as n plus 1 by 2 square minus n minus 1 by 2 square. So we'll simplify this right hand side, then we'll get this left hand side, and that is n. So that means any odd number can be expressed as difference of squares of two numbers. But in this question it says a and b are positive integers. So we'll take n as 1. In that case, we'll get it as 1 square minus 0 square. So except for n equals 1, all other odd numbers can be expressed as a square minus b square. So that means the only odd number that we'll get in this series is n equals 1. Now if n is not odd, then n will be even. Now there are two kinds of even. One which are of the form n equals 4k, and then the numbers which are of the form n equals 4k plus 2 when n is greater than 4. Now we know that if n is equal to 4k, then we can write n as n by 4 plus 1 square minus n by 4 minus 1 square. Now here everything will cancel out, and then we'll get this n. That means any number which is of the form 4k, it can also be expressed as difference of two squares. So that means the numbers which cannot be written in the form a square minus b square will have to be of the form n equals 4k plus 2. Now in this question, it cannot be an odd number except for n equals to 1, and then it has to be some even numbers which are of the form 4k plus 2, but it is when n is greater than 4. Now it cannot be true for 3, so the only point that we need to check is at n equals 2. Now we cannot express 2 as a plus b into a minus b, because parity of a plus b and a minus b will be same. Either both of them they'll be odd, or both of them they'll be even. So both of them, if they are even, then it cannot be 2, and if both of them they are odd, then this number again cannot be 2. So that means 2 cannot be expressed in the form of a square minus b square. So all the numbers which cannot be expressed in the form of a square minus b squares are starting with 1 and then 2, and then all the numbers which are of the form 4k plus 2, that is 6, 10, and so on and so forth. That is the answer to this question. Now question number 6 is a complex equation, and it is z to the power 2018 is 2018 to the power 2018 plus iota. So what we'll do is we'll express this number in polar form. So we'll write its r will be under root of 2018 to the power 2018 whole square, and then plus 1, and then we can write its theta, and it'll be 10 inverse 1 upon 2018 to the power 2018, and this is very small number, nearly equal to 0. So it is some positive number that is nearly 0. So now we can express this equation as z to the power 2018, and this is equal to r into e to the power iota. Now since we need 2018 roots, we can write this as 2k pi plus theta, and then z will be r to the power 1 upon 2018 e to the power iota 2k pi plus theta upon 2018, where the value of k, it starts from 1 and it goes all the way up to 2017. Now the first question is, how many complex solution does this equation have? So any equation of degree n will have n complex roots. So that means this equation will have 2018 roots. Now out of these 2018 solutions, how many solutions will lie in first quadrant? So any solution will lie in first quadrant if its angle lies between 0 and pi by 2. So from here we can write 0 is less than 2k pi plus theta upon 2018, and it should be less than pi by 2. Now this theta is very, very small but a positive number. So we can write this as 0 is less than equal to 2k pi upon 2018, and it is less than pi by 2. So we can write 0 is less than k is less than 2018 divided by 4. So it'll be 0 and then k, and it'll be 504 0.5. So k can take all the values starting from 0 to 504. So that means number of solutions that lie in first quadrant will be 505. So there will be 505 solutions in first quadrant. Now it says how many solutions lie in second quadrant. Now for second quadrant, this value, it must lie between pi by 2 and pi. So we can write pi by 2 and it is 2k pi. So we'll approximate it upon 2018 and it is less than pi. So again we'll write 2018 divided by 4 is less than k is less than 2018 divided by 2. So it'll be 504.5 and then k and it'll be 1009. So number of integral values of k which lies in this interval is 504. So this equation will have 504 solutions in second quadrant. Now question number 7, it says let x cube plus ax square plus bx plus 8 equals to 0 be a cubic equation with integral coefficients. Suppose both r and minus r are roots of this equation where r is greater than 0 is a real number, then list all possible pairs of values a and b. Now suppose roots are r minus r and s. Now we'll write s1, that is sum of all the roots, then it'll be r minus r, it'll cancel, so it'll simply be s and it'll be equal to minus a. Now we'll write s2, it'll be rs minus rs, so it'll cancel and then we'll get minus r square and this is equal to b. And the same way we can write s3 and which is product of all the roots, so it'll be minus r square s and this value will be equal to minus 8. So from here we can say r square s equals 8. So we have 3 equations. Now b is minus of some perfect square. So from here we can say this b is actually less than 0. Now r square into s is equal to 8. So it means this s, it is greater than 0. And if s is greater than 0, a is minus s. It clearly means that a is also less than 0. So from here we'll get this condition as a should be negative and b should be negative. Now if we'll put the value of s and r in this third equation, we can write s into r square. S into r square is simply a into b. So product of a, b, it should be equals to 8. So now we need to find the values of a and b such that their product should be 8 and they are integer numbers. So we can express 8 as 1 into 8 and 2 into 4. So the possible solutions are either a is minus 1, b is minus 8, a is minus 2, b is minus 4, a is minus 4, b is minus 2, or a is minus 8 and b is minus 1. So we have these possible pairs of a and b. Now question number 8, it is very interesting question. It says how many non-congruent triangles are there with integral lengths a less than equal to b is less than equal to c such that a plus b plus c is equal to 20. Now since a, b, c, they are sides of a triangle, they cannot be negative. So what we'll do is we let a as say 1 plus x1 where x1 is greater than or equal to 0. So we have substituted a with 1 plus x1, that is the minimum value of a can be 1. Now b is greater than a, so we can write this b as b equals a plus x2. So that means this b will be at least as large as a. So we can write this as 1 plus x1 plus x2 where again x2 is greater than equal to 0. And in the same way, this c is greater than b. So we can write c as say b plus x3. So which simply means we can write this as 1 plus x1 plus x2 plus x3 where x3 is also greater than 0. Now we are given this condition that a plus b plus c is 20. So we'll add them, then we'll get 3 plus 3x1 plus 2x2 plus x3 and this should be equal to 20. So we can write this equation as 3x1 plus 2x2 plus x3 and it should be 17 where each of x1, x2 and x3 they are integers greater than or equal to 0. So this is the condition that we have when a plus b plus c is 20 and a is less than equal to b is less than equal to c. Now we'll need one more condition, that these three lengths, they'll form a triangle. So three numbers, they'll form a triangle if they satisfy triangle inequality, and which is sum of two sides must be greater than this third side. So that means from here we'll also need to write a plus b must be greater than c. Now what's a plus b? A plus b is 2 plus 2x1 plus x2, and it should be greater than 1 plus x1 plus x2 plus x3. Now here x2 will cancel, x1 will also cancel once. So simply we can write 1 plus x1, it should be greater than x3. So we need to find solution to this equation provided x3 is less than 1 plus x1. So now we'll put in the values of x1, x2 and x3, and then we'll see how many such triangles are possible. So we'll consider the values of x1, x2 and x3. Now we'll take x1 as 0. Then in that case, we'll get this equation as 2x2 plus x3 is equal to 17. Now we also know that x3 is less than 1 plus x1. So that means x3 is less than 1. So the only value possible for x3 is 0. Now x3 has to be an odd number to get an integral solution. So that means for x1 equals to 0, we won't get any solution. Now when x1 is equal to 1, we can write 2x2 plus x3, and this is 17 minus 3. 17 minus 3 is simply 14, where x3 is less than 2. Now in this case, 2x2 plus x3 is 14. So that means x3 can take only even values. So the only even value possible in this case is x3 equals 0. So that means we have one triangle in which x1 is 1, x3 is 0, and if we'll put x3 as 0, we'll get x2 as 7. Now we'll take x1 as 2. So we'll take x1 as 2, we'll write 2x2 plus x3, and it'll be 11. And here x3, it is less than 3. Now again x3, it has to be an odd number. So the only odd number possible in this case is x3 equals to 1. So that's our second triangle possible. Now we'll take x1 as 3. Then it will be 2x2 plus x3 equals to 8, where x3 is less than 4. Now here x3 has to be an even number. So we have two values of x3 possible. Either x3 is 0 or x3 is 2. So it will give us two more triangles. Now we'll take x1 as 4. Then we can write 2x2 plus x3 is equal to 5. Now where x3, it should be less than 5. Now x3 take odd values. So value of x3 can be either 1 or value of x3 can be 3. So we have two more triangles. And then finally we'll have x1 equals 5. So we'll get 2x2 plus x3, and this is equal to 2, where x3 is less than 6. Now in this case, x3, it has to be an even number. Since this value is 2, so x3 can take only two values, and which is either the value of x3 is 0 or the value of x3 is 2. So we'll need to count number of triangles possible. So we have one triangle here, and then we have one triangle here. We have two triangles here, two more, and then finally we'll have two more triangles. So it'll be 6 and 2, 8. So number of such triangles possible is simply 8, and that is the answer to this question. Now question number 9 is, consider a sequence of polynomials with real coefficients defined by p0 x equals x square plus 1 into x square plus 2 up to x square plus 1009. So we'll find degree of p0. So degree of p0 x will simply be x to the power 2018. Now if we'll consider, say, p1x, so p1x will be p0 x plus 1 minus p0 x. Now p0 x plus 1 minus p0 x will be a polynomial of degree 1 less than degree of p0. So its degree will be 2017. So in the same way we can say this pnx, it will be a polynomial whose degree is 2018 minus n. Now consider an equation which is Pnx minus Pn1 equals to 0. Now degree of this equation will again be 2018 minus n. Now in the question it says P1 equals P2 equals P5000. So that means this equation will have at least 5000 real roots. Now degree of this polynomial is 2018 minus n, which is obviously less than 2018. And this equation has more than 2018 roots. So it can only be possible when this Pnx is a constant function. So if it is constant function, then degree of Pnx must be 0. So that means the value of n should be 2018. So answer to this question is the least value of n is simply 2018. Now question number 10, it says, recall that sine inverse t, which is arc sine t, is a function with domain -1 to +1 and range -π/2 to +π/2. Now it says consider the function fx, which is sine inverse of sine x, and then we'll need to find whether these three statements they are true or false. So what we'll do is in this question we'll draw the graph of sine inverse of sine x. So we have already discussed the graph of sine inverse of sine x in one of the previous videos when we were discussing graphs. So I'll put the link to that video in the description below. So we'll draw the axis. And then for sine inverse, principal value range is -π/2 and +π/2. So we'll draw -π/2 and +π/2 on both the axes. Now between -π/2 and +π/2, it will simply be x. And then we'll keep drawing these zigzag lines. So that is the graph of sine inverse of sine x. Now the first question is, the function fx is well defined for all real numbers x. The domain of this function is simply x belongs to R. So that means this function is well defined for all real numbers x, so which is true. Now the second is, the function fx is continuous wherever it is defined. So this function, it is continuous for all x belongs to R. So this is also true. Function fx is differentiable wherever it is continuous. So at these points, we know that we have two different tangents. So that means this function, it is continuous for x belongs to R, but it is not differentiable odd multiples of π/2. So that means third statement is simply false. So answer to this question is true, true, and false. Now we'll come to part B questions, and it says a natural number k is called stable if there exist k distinct natural numbers a1, a2, ak, each ai greater than 1 such that 1 upon a1 plus 1 upon a2 plus 1 upon ak is equal to 1. So it says that show that if k is stable, then k plus 1 is also stable. Using this or otherwise, find all the stable numbers. Now we know that it cannot be true for k equals 1. So we cannot write 1 upon a1 equals to 1 when a1 is unequal to 1. So that means k equals to 1 is not stable. What about k equals 2? So we'll take k equals 2, we'll get 1 upon a1 plus 1 upon a2, and this value, it should be equal to 1. Now this again is possible only when we have both the numbers same, but then it says it is stable if there exist distinct natural numbers. So that means k equals to 2 is not stable as well. So we'll start with k equals 3. Now we know that we can write 1 as 1 by 2 plus 1 by 3 plus 1 by 6. So that is, it is possible to express 1 as sum of 1 upon a1 plus 1 upon a2 plus 1 upon a3, where each of a1, a2 and a3, they are distinct and they are greater than 1. So now we'll solve this question using induction. We'll solve it for k greater than or equal to 3. Now this is our first case. So this statement is true for k equals to 3. Now we'll let it be true for n equals k. If it is true for n equals k, then we can write 1 upon a1 plus 1 upon a2 plus 1 upon ak, and this value is equal to 1. Now using this result, we have to prove that it is true for n equals k plus 1. So what we'll do is, in this we'll divide everything with 2. So we'll divide everything with 2. We'll get 1 upon 2a1, 1 upon 2a2 and 1 upon 2ak, and this is equal to 1 by 2. Now we'll add 1 by 2 both sides. Then we can simply write 1 by 2, 1 upon 2a1, 1 upon 2a2 plus 1 upon 2ak, and this is equal to 1. And now we have k plus 1 distinct numbers. So that means this statement is true for n equals k plus 1. So from induction we can say that this statement or this condition is true for any value of k which is greater than or equal to 3. Now question number B, it says, let f be a differentiable function defined on subset A of real numbers such that this f star y is maximum of x belongs to A, yx minus fx whenever the above maximum is finite. Now for the function fx equals minus log x, determine the set of points for which f star is defined and find an expression for f star y involving only y and constants. Now for this function, we are given fx as minus log x. So now we can write f star y as maximum x belongs to A, and here it will be yx, and in place of fx we'll write minus ln x. So it will be plus ln x. Now we'll differentiate it with respect to y. So it will be df star upon dy, and will be simply maximum of x belongs to A. Now it is y and then plus 1 upon x. Now domain of this function fx is x is greater than 0. So we have two separate cases. Case 1, if y is greater than or equal to 0, then this y plus 1 upon x, both of them, these values, they will be positive. So in this case, df star upon dy, it will be greater than 0. Then in that case, this f star will be strictly increasing function, and if the function is strictly increasing, then we do not have a global maximum. So we do not have any function defined for y greater than or equal to 0. Now when y is less than 0, in that case, if we'll find its critical point, we can write df star upon dy equals to 0. So from here we'll get y plus 1 upon x equals 0. So we'll get x as minus 1 upon y. So it'll be minus 1 upon y, rightmost negative, and this is positive. So it will have a local maximum at x equals minus 1 upon y. So now in this case we can write this f star y as, now in place of x we'll write minus 1 upon y. So it will be minus 1 minus f minus 1 upon y. So this function is defined when y is less than 0, and will be f star y equals minus 1 minus f minus 1 upon y, and when y is greater than or equal to 0, this function is not defined. Now question number 2, part A is, find all real solutions of this equation x square minus 2x to the power x square plus x minus 6 is equal to 1. Now we know that a to the power b is equal to 1 when either a is 1 or when a is minus 1 and b is an even number, or when b is 0 and a is unequal to 0. So we have these three cases. So we'll take this first case when a is equal to 1. So it simply means x square minus 2x is equal to 1, or we can write x minus 1 whole square equals 2. So value of x is 1 plus or minus under root 2. Now the second case when a is minus 1. So x square minus 2x is equal to minus 1. So from here we'll get x minus 1 equals to 0. So here the value of x is 1. And if I'll put value of x as 1, then the power will be minus 4, which is an even power. So another solution is when the value of x is 1. And this third case when this power is 0. So this power is 0 when x square plus x minus 6 is 0. And with that, x square minus 2x should not be 0. So we'll get x plus 3, x minus 2 equals 0. So either the value of x is minus 3 or the value of x is 2. And from here we'll get x is not equal to 0 and x is not equal to 2. So from here we'll take only this solution, which is x equals minus 3. So this equation has 4 solutions. Either the value of x is 1 plus minus root 2, or the value of x is 1, or the value of x is minus 3. Now question number B, it says we need to find the value of this expression. Suppose this value is x. So we'll take cube both sides, then we can write x cube, and this is a cube. So this is 6 root 3 plus 10 minus 6 root 3 minus 10, and then minus 3, and then cube root of, so this is 36 into 3, 108, 108 minus 100, so it will be simply 8, and then it will be cube root of 6 root 3 plus 10 minus cube root of 6 root 3 minus 10. So we can write this as x cube. Here 6 root 3 will cancel, so it will be 20, and then minus 6, and this is nothing but x. So we'll get this equation as x cube plus 6x minus 20 equals 0. Now it's a cubic equation, so we'll put x as 2, we'll get 8 plus 12 minus 20 equals 0. So one of the root of this equation is x equals 2. So now we'll use synthetic division. So this is 1, 0, 6 and minus 20, and this is 2. So this is 0, 1, 2, 2, 4, and then 10. It is plus 20, and this is 0. So we can write this as x minus 2, and then x square plus 2x plus 10 equals to 0. So the only real value of x we'll get from this expression is 2. So answer to this question is the value of this expression is 2. Now question number 3, it says a function f is defined on non-negative integers, and it is defined as f2n equals f of fn and f2n plus 1 equals f2n plus 1. Now it says if f0 is 0, then find fn for every n. So from f0, which is f0 equals 0, we can find f1 if I'll put n as 0. So f1, it will be f0 plus 1, and f0 is simply 0. So f1 is 1. Now we'll find f2. So if we'll put n as 1, we'll get f2. So it'll be f of f1, and f1 is simply 1. So it'll be f1, and f1, it is simply 1. Now we'll find f3. f3 will be f2 plus 1. The value of f2 is 1. So it'll be simply 2. We'll find f4 also. So f4, it will be f of f2. Now the value of f2 is simply 1. So it'll be f1, and the value of f1 is simply 1. So now we'll keep getting the same pattern. So we know that f0 is 0, f1 is 1, and f2 is 1. So we can write this function fn as 0. When n is 0, it is 1. When n is 1, and it is 1. When n is equal to 2. Now when n is greater than 3, then if it is of the form 2k plus 1, where k is greater than or equal to 1, then in that case its value will always be 2. And if n is of the form 2k, when k is greater than 1, its value will be 1. So this is how we can define this function fn. Now part B, it says show that f0 cannot be 1. So we'll prove this by contradiction. So we'll let f0 is equal to 1. So if I'll put n as 0, then we can write f0 is equal to f of f0, and value of f0 is 1. So from here we'll say the value of f0 is equal to f1, and the value of f0 is simply 1. So from here we'll get this condition as the value of f1 is equal to 1. Now we'll also find the value of f1 from this second equation. So we'll put n as 0 here, we'll write f1, and this is f0 plus 1. Now f0 is 1, so from here we'll get f1 is 2. So f1 cannot be 1 and 2 simultaneously. So that means our supposition is wrong. So it implies that this f0 it cannot be 1. Now we'll come to its third part. It says, for what non-negative integers k, if any, can f0 be equal to 2 to the power k? So let f0 equals 2 to the power k. Now we can write f1 as f0 plus 1. So it will be 2 to the power of k plus 1. Now we'll write f2. f2 simply will be f of f1, and f of f1 simply will be f of 2 to the power k plus 1. Now how do we find f of 2 to the power k plus 1? So we'll put n as 2 to the power k minus 1, then we'll get f of 2 to the power k plus 1. So then in that case it will be f of 2 to the power k plus 1. So now from this first equation we can also write f2n is equal to f of fn, f of 0 equals f of f0. Now f of 0 is 2 to the power k, and this is f of 2 to the power k. So from here we can say that f 2 to the power k is same as 2 to the power k. So from here we can write f2 as 2 to the power of k plus 1. So we'll continue like that. Then we can simply say then f 2 to the power n will simply be 2 to the power of n plus 1. But we have already established that f 2 to the power n is 2 to the power n and not 2 to the power n plus 1. So we get a contradiction here. So again from this case we can say that f0 can never be 2 to the power k. So again, there is no non-negative integral value of k for which f0 is equal to 2 to the power of k. Now in question number 4 it says, let ABC be an equilateral triangle with side lengths of 2, points A dash, B dash and C dash are chosen such that A dash B is k. Likewise, B dash and C dash are chosen on sides C and AB with CB dash and AC dash equals k. Line segments are drawn from points A dash, B dash and C dash to their corresponding opposite vertices. The intersection of these line segments form a triangle PQR. We need to show that this PQR is an equilateral triangle whose side length is 4 1 minus k upon k square minus 2k plus 4. Now it says A dash B is k. So this is A dash B, it is k. Then A dash C is 2 minus k. In the same way, C dash B is k and AB dash is 2 minus k, AC dash is k and BC dash is 2 minus k. Now from this figure we can say that these three triangles A dash B, that is this triangle, it is congruent to this triangle which is B dash C, and it is congruent to this triangle which is C dash A. So if these three triangles are congruent, it simply means these angles they are equal. And if these angles are equal and length of these sides is k, so then from here we can also say that the triangle APC dash is congruent to triangle BQA dash is congruent to triangle CRB dash. So these three triangles, they are congruent. If they are congruent, that simply means these three lengths they are same, and also these three lengths they'll be same. Now since triangles A dash B, B dash C and C dash A, they are congruent, from here we can say that A dash is equal to B dash is equal to C dash, and from this second result we can say that this AP is equal to BQ is equal to CR, and PC dash is same as QA dash is equal to B dash R. So if we'll subtract AP and QA from AA dash, we'll get PQ. So from here we can say this PQ is same as QR is same as RP. So that means this triangle PQR, it is an equilateral triangle. Now we need to find length of side of this equilateral triangle. So what we'll do is we'll drop a perpendicular from A to BC. Now suppose this point is O. Now we can write this AA dash as, so AA dash square is equal to AO square plus OA dash square. Now this is AA dash square. Now AO square. AO is altitude of this equilateral triangle. This angle, it is 60 and side length is 2. So 2 sine 60 is root 3. So it will be simply root 3 square and plus OA dash. Now this is midpoint. So this length is 2. So this is 1 minus k. So it will be simply 1 minus k square. So from here we can say AA dash will be simply under root of k square minus 2k plus 4. So that is the length of this AA dash. Now if we look at this triangle ABA dash and triangle BQA dash. So we can prove that these two triangles, they are similar. So in this triangle we know that this angle alpha is equal to this angle alpha. So this is angle alpha. Now this angle, it is 30 minus alpha. So this angle will be 90 minus 30 minus alpha. So it will be 60 plus alpha. Now this exterior angle is equal to angle Q plus angle alpha. So this angle will be 60. So this angle BQA dash and this angle B, they are both 60. So from A property, we can say that these two triangles ABA dash and BQA dash, they are similar. Now if these two triangles are similar, then we can simply write AB upon BQ is same as BA dash upon QA dash, and this is equal to AA dash upon BA dash. Now AB is 2 and we need to find BQ. BA dash is simply K upon QA dash. A dash we have worked out, so it is under root of K square minus 2K plus 4, and BA dash is simply K. So from here we can say value of BQ is 2K upon under root of K square minus 2K plus 4, and value of QA dash is K square upon under root of K square minus 2K plus 4. So now we can write this AA dash as AP plus PQ plus QA dash. So AA dash is simply under root of K square minus 2K plus 4, and this is equal to AP. Now this AP, it is same as BQ because we have already proved that these three triangles, they are congruent. BQ in this case is 2K upon under root of K square minus 2K plus 4 plus PQ. Now QA dash is simply K square upon under root of K square minus 2K plus 4. So we'll take everything on the left hand side. We can simply write this PQ as K square minus 2K plus 4 and then minus 2K minus K square upon under root of K square minus 2K plus 4. So which is K square will cancel. So we'll get this is 4 minus 4K, which is 4 1 minus K upon under root of K square minus 2K plus 4. So we have proved that it is an equilateral triangle and its side length is 4 into 1 minus K upon under root of K square minus 2K plus 4. Now question number 5, it's an interesting permutation combination problem. It says an alien script has n letters b1, b2 up to bn. Now for some k less than n by 2, assume that all words formed are meaningful. These words are called k words. A k word is considered sacred if no letter appears twice, and if a letter bi appears in the word, then the letters bi minus 1 and bi plus 1 do not appear. Now here it also says bn plus 1 is equal to b1 and b0 equals bn. So that means we have arranged these n letters in some sort of a circle. So we have these n letters which are arranged somehow in a circle: b1, b2, b3, and then we have bn. Now what is the total number of sacred k words that can be formed? And we need to use this formula to find the answer for n equals 10 and k equals 4. So a word is called sacred if no letter appears twice. So that means we have to select k letters such that each letter is selected only once, with the condition that if a letter bi is selected, then bi minus 1 and bi plus 1, they are not selected. So basically it is a problem of non-consecutive selection on a circle. Now since all these letters, they are arranged on a circle, we know that on a circle all the arrangements are relative to some particular specific position. So what we'll do is we'll first mark any one element that we are going to choose. So from these n elements, we'll select one element, and it can be done in NC1 ways. So first we'll choose any one number. Suppose we choose B3. Now we have to choose remaining k minus 1 numbers from n minus 1 numbers such that in between any two selections, there is at least one letter. So suppose after B3, we select some other number and then some other number and then some other number. Now say in between first and second selection, we have x1 letters. In between second and third, we have suppose x2, and in the same way, and in between the last pair, we have this selection which is xk. So that means we can write this in terms of linear equation, which is x1 plus x2 plus xk, and it should be equal to, now what is the remaining number of elements? Remaining number of elements is simply n minus k. So from these n letters, we have selected k letters. So all these remaining letters, they have to be distributed in such a way that x1 plus x2 plus xk should be equal to n minus k, where each of this xi should be greater than or equal to 1. Because in between any two selection, there has to be at least one letter. We know that number of positive integral solution to this equation is given by nc1, and it is n minus 1, which in this case is n minus k minus 1, c r minus 1. R is k, so it will be nc1 into n minus k minus 1 c k minus 1. Now we can arrange these k numbers in factorial k minus 1 ways. So the total number of sacred k words that can be formed is given by this formula, which is nc1 n minus k minus 1 ck minus 1 into factorial k minus 1. Now we can put in the value of n as 10 and value of k as 4, and then we can find the answer to this question. Now question number 6, it is sort of a puzzle. It says, imagine a unit square in the plane to be a carom board. So it is a unit square. So this length is 1 and this length is also 1. Assume the striker is just a point moving with no friction, and that when it hits an edge, the angle of reflection is equal to angle of incidence as in real life. If the striker ever hits a corner, it falls into the pocket and disappears. The trajectory of the striker is completely determined by its starting point xy. So suppose we have any striker, then trajectory is determined by this point, which is x comma y, and also its initial velocity, which is pq. So p in horizontal direction and say q is in vertical direction. If the striker eventually returns to its initial state, we define its bounce number to be number of edges it hits before returning it to the initial state for the first time. So suppose, for example, there is a striker which is at 0.5, 0.5, that is center of this board, and has a velocity 1, 0, that is it is headed in the x direction. So first it will hit this edge and then it will rebound, and again it will hit this edge and then it will come to the same position with same velocity. So in that case, this bounce number, it will be 2. In the same way, it says for initial state 0.25 and 0.75, it has bounce number of 4. So this is how this particle is going to bounce back. Now the first question is, if the striker has initial state of 0.5, 0.5 and velocity of pq, so if p is greater than q, what is its velocity after it hits an edge for the first time? And if q is greater than p, what is its velocity? So we'll consider this carom board. Now we have this striker which is at 0.5, 0.5, and this is y equals x line. Now we know that if a striker hits horizontal edge, then after reflection, its velocity, which is pq, will change to minus p and q. So only the horizontal component of the velocity will change, vertical component will not change. And if the striker hits the vertical column, in that case, only the vertical component is going to change, horizontal component won't change. So in that case, it will change from pq to p comma minus q. Now first question is, if p is greater than q. So if p is greater than q, so that means this angle, it is less than 45 degrees. So if p is greater than q, in that case, its velocity will change from pq to minus p and q. So it will be true when p is greater than q and it is greater than equal to 0. And if q is greater than p, which is greater than equal to 0, then in that case, it will hit a vertical edge. The velocity will change from pq to p minus q. Now question number B is, draw a trajectory with bounce number of 5 or justify why it is impossible. Now we know that after any bounce, only one of the component will change. So if initial state is pq, then after say m horizontal reflections and n vertical reflections, its velocity will be minus p to the power m and minus q to the power n. Now it should be equal to p and q. It'll be same as p and q when both m and n, they are even numbers. So if m and n, they are even numbers, then bounce number cannot be an odd number. So bounce number of 5 is not possible. Now question number C, it says, consider a trajectory with initial state x, y and velocity is p comma 0. So here, suppose we have any position, say x comma y, and velocity is in the horizontal direction and it is p. Now we need to find the time that the striker takes to return to its initial state. So the striker, it has to cover this distance twice and this distance twice. So this striker has to cover a distance of actually 2 units with the velocity p. So time taken to complete this journey, it will simply be distance upon speed. So this is 2 upon p. So time taken by this striker to return to its initial state is 2 by p. Now we'll come to its fourth part. And its fourth part is, what is the bounce number for initial state x, y and pq where p and q are relatively prime positive integers, assuming that striker never hits a corner. So a striker starts from xy and it returns to xy with same velocity. Now we know that in any horizontal bounce, time taken to complete one journey is 2 upon p, and so this is t horizontal, and time taken to complete one vertical journey is 2 upon q. So now let us say that it is after time t, particle returns to its initial state. Now time taken to complete one horizontal journey is 2 upon p. So number of horizontal trips in time t, it will be given by t upon 2 upon p, which will simply be tp upon 2, and number of vertical journeys will be given by t upon 2 upon q. So it will be simply t q upon 2. Now p and q, they are relatively prime. So that means this 2, it must divide t. So this t, it should be some multiple of 2. So the minimum value of t in this case will be simply 2 minutes. So it is when the time is 2 minutes, this striker, it will return to its initial position, giving nh and nv as integral numbers. So if the time is 2, now we can find bounce number. Now we need to find bounce number for the striker. Now bounce number for the striker will be 2 times number of horizontal trips and number of vertical trips. So number of horizontal trips will simply be P and number of vertical trips will be Q, and in each trip there will be 2 bounces. So bounce number for this trajectory will be 2P plus 2Q, and that is the answer to this question.